Welcome to this introductory video on Group E 2026's low-power IoT sensor system. The big work that is the low-power IoT sensor system is, in short, a wireless low-power sensor system reading changes in a building environment using a database and dynamic wireless node structures to transmit and provide remote clients with a reliable, secure, visual, and user-friendly overview of their data and room state. We'll start by looking at the architecture of the system. Primarily, there are 6 modules in the system. We'll start at number 1, sensor node. This is a hardware module that is mounted at a point, example a door, where its sensor can collect data and transmit wirelessly this data to a gateway or collector. At number 2, we have the gateway or collector, which is another hardware module that collects data and communicates with one or more nodes. Number 3, we have the uplink, which is yet again another hardware module, which can be considered a part of the gateway. The uplink is in this low-power IoT sensor system only used as the gateway does not have Wi-Fi capabilities needed for direct connectivity to the database. The database is used for storage of the node's sensor data and is cloud-based. Number 5, we have the backend, and at 6, the frontend. The data from the database is downlinked to a server which interfaces with a web browser through a secure socket. This creates a wireless sensor system where the data streams goes from the low-power MCU, also called a node, to a collector or gateway, which is connected to an uplink that connects the physical node's gateway and uplink to the internet, where the data ends at the end client's web browser. Later in this video, the link will be shown, where the node will send a message from approximately 9 meters distance to the gateway. The web browser will also be shown with the real node data. The system will have multiple nodes to each gateway and employ a star network topology with sleepy end nodes as an architecture. This architecture, presented here as the black box being the gateway and the blue circles being the node, gives a high number of nodes per gateway as the node spends most of their time sleeping, something that is also very beneficial to the node's battery. Traditional wireless communications between the node and the gateway, like Wi-Fi or Bluetooth, for the system was considered, but a sub-1 GHz radio configuration was chosen as it used not only power in transmitting, but also had a good signal integrity. The system's low power consumption and good signal integrity meant that the part of the system most physically exposed would need zero maintenance for a substantial amount of time and have a robust connection to the gateway.
The ESP32 is an integral part of the system, acting as the uplink between the gateway and the database. This means that it carries the data received from the gateway over to Firebase by processing and formatting it for further usage by the Firebase database. The ESP32 microcontroller was chosen as the uplink node because of the performance advantage at a low price compared to similar microcontrollers. Other considerations include the ESP8266 and similar performing boards, but we found the added core on the ESP32 such an advantage in offloading the Wi-Fi workload that we prioritized it. The more powerful Raspberry Pi 3B Plus model was also considered, giving a huge performance overhead, but was concluded to be unnecessarily powerful for our system. At a very high increase in price, we could not justify it if low cost was to be a selling point. The communication between a gateway and an uplink is established by utilizing the UART protocol. This keeps the setup for the system simple, yet powerful enough to transmit the information in an uninterrupted manner. This limits the number of physical pins needed to only one, as we only utilize simplex as this time, although half duplex is possible if needed. The advantage this setup gives is the asynchronicity, exempting the need for any shared clock. The system instead uses start and stop bits to declare each package, which enables communications as long as the baud rate is set as the same. Another advantage of the use of UART is the possibility to read the serial output via a computer using an USB connection, making troubleshooting easier. The uplink receives a string in the format NodeID: value 1, value 2, etc., which is defined as the standard format between the gateway and the uplink. The string is processed by separating the node ID and each value to its own entity. After these operations, each value's address is created by appending the node ID to the value name, such as temperature, battery, etc. The uplink then handles the sending of each value, categorized under the node ID with the correct value name. It is then easy to access the value one would wish to display by entering the Firebase database's website and expanding the node ID, then expanding the value name. Multiple libraries are utilized to set up the functionality of the uplink, such as the standard stdlib.h, wifi.h, and string.h, and the specialized Firebase ESP32.h library. Combining these keeps the processing simple, while still remaining intuitive to work with. Each of these enables certain functions for a system which are necessary for optimal performance. stdlib.h and string.h enables proper string parsing, which is needed for the Firebase ESP32.h library. Firebase ESP32.h includes pre-made functions for easily handling correct transmission of the data to the database, by converting the input values to JSON format, which is the accepted format by the database. Wifi.h allows connection to any Wi-Fi network which is needed to connect our Firebase system. The code is mainly in the C programming language, as it was considered the most optimal language for the project. It keeps the coding at a low level, allowing fast operations and more control of the handling of the incoming strings. By keeping the functions at a hardware-near level, it is easier to properly troubleshoot any occurring problem, as one can apply hardware logic to the functions by trying to think as a computer would accept the incoming data. This way, one can easily understand what causes any error and how one could prevent them from happening any further.
The database used in this thesis was used to store sensor data and had an easy and secure solution for updating and downloading this data. It was also a real-time cloud storage platform which was easily accessible worldwide. It had a low downtime and offered safe access to requests and responses from other modules. Furthermore, it interfaced with the uplink and used a shared data transformation protocol. The database featured security features which was to be used in conjunction with other further security layers in the backend. Lastly, the database was selected due to having an easy way of formatting the hierarchical data. Further utilize the data in the backend and the user-friendly cloud interface. The database included a REST endpoint that may be accessed through the HTTPS protocol by computers and simple devices such as microcontrollers. For applications with less data processing requirements, connecting and interacting with Firebase as a REST endpoint may be advised. It was a lightweight and simple way of interacting with the database that did not require any further library support than the HTTPS requests and responses, thus not requiring languages such as JavaScript and a runtime environment such as Node.js. This duality allowed both simple uplinks and more complex applications such as Node.js to both interact with Firebase unhindered, which was a key point in the choice of database. The backend was designed to serve a real-time connection between the database and the frontend. It was designed to be able to serve the frontend with web content, such as HTML, where the web content served includes a real-time representation as close as possible of the sensor data acquired from the database. The backend was designed to be easily accessible by the frontend and introduce as little as possible time latency before posting the data from Firebase onto the web page. The backend has been designed to forward new data only on updates, meaning the backend was designed with a non-polling, such as interrupt-based architecture, which reduced unnecessary stress on the database. The backend also processes the raw sensor data before forwarding the result via a real-time socket to the frontend. The frontend was designed to maintain a real-time connection with the backend, where the web page was designed to be user-friendly and a simple interface during development and production. The frontend was designed to communicate with the backend through a real-time socket, which were used to update the sensor data displayed. It introduced an index page or home page, featuring the links to all the discrete subpages, whereas all nodes in the database were given their own discrete subpage. These subpages displayed the relevant sensor data for the given node. The page was intended as a proof of concept and was not given a particularly fancy design. It follows an easy Scandinavian design philosophy.
This is the hardware section. I'll go over the physical results of our thesis. To the right you can see a layered view of the final prototype PCB that was manufactured. This is the final PCB that we made. It measures about 6.5 cm in width and is 7.2 cm in height. Power routing was mostly done on the back side. The RF power line and the VCC power line is visible here. We have two big ground planes and most of the signal routing is done on the top side, as you can see here. The specifications is as follows. We have a CC1312R as our main MCU. It has a built-in temperature sensor, which we are using. It has embedded software, which has voltage calibration curves, so that we can calibrate the sensor more accurately. It also has a brightness sensor located here. It uses the I2C standard and has an interrupted pin, so we can make the MCU sleep when it's calibrating the value. It has 6 door switches here, which are general I/O pins, but we use it for the door switches. It also has 1 pin for VCC and 1 pin for ground. We also have a dB sensor here. It consists of a mic, an op-amp and some filters, and an inverting circuit, which you don't have to install. It also has a bypass resistor here. It also has an adjustable gain used by this pot meter here, which is a part of the calibration potential meters, which we use for both the temperature sensor and brightness sensor, and a threshold for noise. We have 8 dip switches. 6 of them are used for each of the I/O here, and one of them is used to select which accuracy to use for the brightness sensor. We have a DN038 antenna, a PCB antenna, and we have a CR2032 battery, which is a commercially very available battery. It has a lifespan of about 10 years in our use case, and we have a custom-made pairing port. The pairing port is used to pair the node to the master node's network. This one is custom-made and has a detection circuit on the master node side. It can detect if it is inserted the wrong way and protect both units. It also has standard JTAG interface, which uses the same pinouts as the Launchpad series. And we have a few debug LEDs here, which is enabled by this pin here. You just short the header. This is the 3D design of the casing used. This was made in Fusion 360. The top one here has a hole for the brightness sensor here and here, and has slots here for the microphone, also located here. The bottom part has 4 holes for mounting the PCB and 2 holes for mounting it onto a wall. It has a hole for inserting cables, and it is closed by this extruding part on the top side. It will need to be cut manually to allow cables to get in, which will make it more dust-proof. And that's it for this physical part.
The result is a proof of concept, however not a commercialized solution. The system was successful in monitoring the door state and temperature in a room in Uppdal, with data presented in real time at roughly 1 second latency on a web browser in Trondheim. The goal of a low-power smart sensor IoT system has thus been achieved, and a proof of concept presented. The current system may transmit the state of a reed switch sensor along with battery level, brightness of the room, noise, and temperature of the CC1312R chip. The current system may transmit the state of a reed switch sensor along with battery level, brightness of the room, noise, and temperature of the CC1312R chip. The only requirements for the end client is a web browser and a Wi-Fi connection. Several roadblocks were met during the development of the system, including highly varied programming languages, hundreds of components, and intricate wireless designs. This is not to say that the current conclusion is an unfulfilled bachelor project, however that the design of a complete IoT system is a complex task. The following recommendations are made for future iterations. For simplicity, use either a Raspberry Pi as the uplink or a microcontroller with both Wi-Fi and sub-1 GHz radio as the gateway and uplink. If cost efficiency is a factor, it is recommended to keep the modular design with an ESP32 or similar as uplink. Carefully weigh any implementations of security layers and encryption between the node and the gateway. To sustain an encrypted channel between the node and the gateway, power consumption on the node will go up. Also limit the number of nodes per gateway. A real-time system link may be achieved without any extra cost, using Firebase real-time database in conjunction with Node.js over a stable Wi-Fi connection. While Firebase provides a safe data storage, having additional security layers inside the on-site server, in our case Node.js, should be enforced before the system rollout.